We understand that defying gravity is very difficult, but we don't see it as an impediment, we see it as a challenge. In taking that challenge, no stride is seen as being too big. We're working on low sonic boom travel so that we can start going faster than the speed of sound. We're working on the next generation air traffic control and heliophysics. We're studying how our sun works. Astrophysics, a big topic there is finding planets around other stars. We're starting to see things on the size of actual Earths around other stars. And on human exploration, the ultimate goal right now is Mars. And so we're putting together all the technology and the science program that leads us on that road. You really can't replace the human presence in the research environment. And research is a part of exploration. You know, I see ourselves in the modern era of Howard Hughes. Howard Hughes inherited a company, it's a drill bit company in Texas from his family. He focused that fortune on aerospace, starting TWA, developing military aircraft, really pushing the aviation world forward in big steps. And we see that today in that there are people like Elon Musk, who made a fortune in PayPal and is now focusing that fortune in aerospace pursuits such as SpaceX. Jeff Bezos from Amazon with Blue Origin, which is a launch company. You see Richard Branson on Virgin Galactic, which is the tourism industry and suborbital and orbital launches. You know they had a passion for aerospace throughout their lives, and they returned to that field. So, you know, that passion for aerospace kindles in all of us.
So I know Dr. David Miller as Professor David Miller. He's been at MIT for more than a decade before I was born. So that's sort of that's primarily because he is what we call an MIT lingo, an MIT lifer, which means he did his undergraduate through his PhD and then stayed as a faculty member at MIT. And in that time, he's influenced probably at least 1,000 students through his hands-on methods of teaching, which you'll probably hear about. And hands-on just doesn't mean hammering in the lab. Undergraduate students who worked with him have built and flown flight hardware. So it's a pretty big deal. But as a graduate student, I would like to share with you two of my interactions or interaction sessions with him in terms of hands-on education outside the classroom, not just inside the classroom. One is Professor Miller would take us to the entire lab to beer every Friday. Every Friday meant as long as he was available and at least 2 or 3 students were available, we'd go out to a bar on campus to talk about not academia, but the context of research in the industry and in the government and so on. And that's incredibly useful because a lot of us spend days and sometimes even years over one equation or one error bar or one plot. And it's very easy to miss the context of that thing in terms of the industry and where it's heading and why it's doing what it's doing. So that was very useful. And the second thing is we have a mission operations room or a center at MIT. It's this big room with a lot of screens, and we are able to talk to mission operations or payload operations at Marshall Space Flight Center in Huntsville, Alabama, to do ISS operations. But by virtue of that, we have these big screens where we can see what astronauts are up to when they're doing payload operations. So Professor Miller would sometimes, every once in a while, host movie night in that mission operations room. And it wasn't just any movie night, it was space movie night, and it used to be space movies and documentaries. And what I got out of that is not just going and watching the Space Odyssey or Star Trek or whatever. It was every time there was a documentary, there were times where Professor Miller would stop it and he would tell us why the camera footage of a rocket is looking the way it's looking, or why something is tilting the way it's tilting, and so on. And I think that was incredibly educational, because even today, when I see Super Stripey go up and I see the camera on Super Stripey tilt too much or spin out of control, I'm like, that rocket's gone. And that's thanks to a lot of the education that Dave has given us. And this would happen at some time in the night, and we'd know the rocket is gone much before the news release the next day. And sometimes I look back and I think that no matter how many equations or textbooks I had read, I wouldn't have known that if it hadn't been for these outside the classroom experiences. So with that, I am going to let Professor Miller take the floor and tell you more about his journey.
Okay.
Thank you, Srija. So thank you for the opportunity today. Charles asked me, you know, got to think of a title, got to think of an abstract, and keep it weird. So I came up with Defying Gravity, and I didn't realize in that clip that, I didn't even realize that clip was out there, but that I said Defying Gravity there, and I like to think of that as what we do in aerospace. It sounds challenging, and that's because it is. But the other part of this is overcoming inertia, which I think has an aerospace tie, but I'm really sort of referring there to the sort of the process of how to get university students into critical path roles. And there tends to be a lot of impediments to that, and I think over history that when we've been able to get students involved directly in critical path roles, there's been a lot of benefit to the whole field of aerospace. So that's what that's in reference to. So I was explaining to a colleague of mine at MIT how he had asked the question, why'd you get into aerospace? And I told him, and he said, oh, so it really wasn't your choice. And no, it wasn't. It was really my mother's choice. He said, you were programmed at a very early age, and that's true. If you start in the upper left here, my mother would keep me home from school during the Gemini launches, and I remember the phone would ring, and the school would be calling up saying, you know, you're depriving your child of an education. And I thought that was my mom thought that was a very poor way to think about it. So it started with Gemini, and then, you know, I watched the Apollo landings and saw 2001 Space Odyssey. I thought we were going to have hotels out of Jupiter by now, but you know, the world was infinite expanse in aerospace. I then applied to MIT, upper right, and I remember my mom said, so you're going, right? You're gonna, when I got the acceptance, she said, you're gonna go. And I was still saying, well, I wanted to look at some other schools. And she said, but why? You're going, right? And I said, I said, yes. So that ended that. Another interesting thing is just before I headed off to MIT when I was 16, she bought me my first motorcycle. And that was because she wanted me to get off the back of her motorcycle. So I guess I sort of had this death grip. And she said, enough of that. You're going to get on your own bike. She also took me out to the airport, local airport at the age of 16, and said, it's time for you to learn to fly. And I was all excited about that. Couldn't wait to tell my dad that night. And he said, it's time you learned how to pay for it. So that put a little bit of a delay into flight. But I really have a passion for aerospace, not only in my intellectual pursuits, but also in my hobbies. And I sort of started here with hang gliders, got myself a hang glider, repaired that hang glider many times. This is not a photo of me, but it represents about my maximum altitude ever achieved in a hang glider. And luckily I don't have any after pictures of that. But then I got into soaring, and I found that, and I tell students, actually, it's pretty funny when students come through my lab, a lot of them have their pilot's license. And like most pilots, you get the license, you spend all that money, you have a piece of paper in your wallet, and you've run out of money. So I encourage people that this is a great way to go because it's like sailing versus motorboating. It really teaches you how to fly a plane. And what I did was I was lucky enough to get involved in soaring competitions. Region 1 soaring, we used to have the competition each year, Region 1 for the US out at Sugarbush, Vermont. And I became the lead meteorologist for the competition. What I didn't realize is no one else wanted the job because it's an interesting job, but I had the opportunity to learn from Bob Buck. So if anyone's a instrument flight, he wrote the seminal book on weather flying, which is sort of must read material for anyone who wants to fly instruments. And he would tell me to call up at the beginning, early in the day, he'd tell me to call up flight service at Burlington, Vermont, and find out what the weather of the day is going to be. So I'd come back with this pages and pages of notes from flight service, and he'd say, now throw that all away. It means nothing to what the local weather in the region was going to be. So that was interesting. But I learned that when you call a competition day poorly, all the pilots throw you in the pond, And then I found out that when you call it well, they also throw you in the pond. So now I understood why it was an easy job to get. I went off to then do power flying, and that's been very rewarding as well. I did spend some time at MIT during this, but I then in academia they promote you based on 3 categories: the quality of your research, your academic innovation, not just your teaching ratings, but how you sort of innovate in teaching, as well as service. And since, as Srija mentioned, I had been there so long, I wanted to do my service outside of MIT. So I joined I'll talk about this a little later, the Air Force Scientific Advisory Board for multiple years, and then made it to NASA headquarters. So it's kind of full closure there. That was nice. So let me start with MIT. Srija sort of stole my joke here, but that's all right. I got my bachelor's, my master's, and my doctorate. They call that MIT cubed, I think, but then I just kept going. And I joined the research staff, and what sort of clinched it was that my advisor had a shuttle experiment, and I sort of saw that I had the opportunity to be a big fish in a small pond, as opposed to vice versa. So I jumped at it, became a faculty member. I'm now the Jerome C. Hunsucker Professor of Aeronautics and Astronautics. Anyone here know who Jerome C. Hunsucker? No. Well, there's an interesting story. After the Wright brothers, basically aeronautics really took off in Europe. And he's the one that went over to Europe and translated a lot of the material. A lot of lightweight structures for wings was written, the textbooks on it were written by Eiffel and others, and he translated that, brought that back into the US and sort of rebuilt aeronautics in the US again. Then the director of the Space Systems Lab. I tell my graduate students, especially those going off into academia, that there are three ways to change the world as a faculty member. One is to write great papers and hopefully someone will read them. The second one is do some consulting and hopefully some company will pick up the idea. But the most important one, though it's a longer time scale, is to train your minions to go out and take over the world. So far I've had 87, I've graduated 87 master's students and 35 PhD students. And as I find now that I'm at NASA headquarters without my students, it really sort of pinpoints that my success is really owed to them. So let me give you the big picture, and then I'm going to zoom in on some of this. I think of myself as an aeroastro professor. I'm also an on-orbit technology lab builder, mostly focused on applications to space telescopes, but I'm also a subject matter expert, and this has really been the service that I've been doing in more recent years. So to give you a little bit of perspective about how I sort of put things together at MIT, I try to make sense of what I do. There's a bunch of different jobs, and I've actually tried to leverage synergies between them. This is one way to look at how I work at connecting the dots. So there are 3 lobes here. The top one is my graduate research program. That's where I have my students, and we work on technology. We also do flight experiments, mostly on shuttle and space station, but now we're moving into small satellites and instruments on large satellites. But I also teach, and in the mid to late 1990s, our department developed sort of revamped its undergraduate education along the lines of conceive, design, implement, and operate. The idea of providing hands-on learning, marrying that with the engineering science that we teach. And this was something that industry and government had pointed out. We had done a survey to see, what do you think of our graduates? And they said, boy, they can really solve equations, but they don't know how to hammer a nail or screw a bolt in or whatever. So I guess you don't screw bolts, so I helped to put together our sort of capstone multi-semester class. And then the other side of it, this was really more of a DoD junior officer kind of program, but to give them flight hardware experience so that mistakes they make would be more $100,000 mistakes instead of $100 million mistakes when they got out to Air Force SMC or elsewhere. And what I saw then I saw, okay, I've got 3 big jobs here. How can I leverage that? Well, I can use them to help me teach this class, and then I can justify that by saying that's leadership. Good. I can use this class to prototype research facilities for my graduate lab, and then I can give them flight program experience by having them use some of those to develop those labs into actually flight programs and operate those. There's another dimension I sort of look through my program. That is starting at the upper row, which is mission analysis, doing system architecture, and you're going to see this theme come back several times through this talk, to try to figure out how you would design missions to do, looking across a variety of missions, ways to instantiate a mission, what's the best way, and then maybe identifying if there are some key technologies that could sort of change the equation, and then try to develop those in the middle row, and then to validate those on orbit. And I'll talk about that next. So starting with the top row, it's really mission analysis, and it's my system architecture work at MIT. What these are supposed to show are just some of these Pareto plots showing some kind of metric of performance versus cost. And we've looked at these for things like the terrestrial planet finder interferometer. We looked at them for reconfigurable constellations in order to increase regional persistence. Also looked at modular space telescopes to try to find out, where in the mass versus line of sight, pointing, where are sort of the optimum designs, and also sparse aperture radar. So we're developing generic tools, but over the years applying them to different areas. So one of the things I realized with the sparse aperture radar and the interferometers is a lot of these were formation flown, and formation flight was, the idea is you use propellant in order to maintain and reconfigure the array. And there was actually a pretty substantial consumption or mass burden associated with using propellant in order to maintain a formation of apertures. So what we thought is there a way that we could actually maintain a formation without using a consumable or a non-renewable consumable such as propellant? So I came up with this crazy idea called electromagnetic wands. I don't know what that meant, but it was sort of the idea, can't we just electromagnetically, let me start the movie, figure out a way to keep these together? Because if we can get rid of the propellant consumption, then maybe we could really save a lot of mass in the system, and we could do a lot more operations. Even though in formation flight, a lot of the delta V it's net zero, but there's a lot of back and forth in motion and control. So what we came up with was, found someone who could make a movie, and said, well, let's think of two satellites that might fly in formation. They got solar arrays. There's nothing else on this satellite except for solar arrays and electromagnets, but this is kind of how we saw it at the time. But you deploy these three magnets, these three sort of electromagnets, and with this, what you're now consuming is electricity that you collect through sunlight, so it's a renewable kind of source. We also said we probably need to use something that can give us a decent field at a distance, so we came up with superconducting magnets. And then if you energize one of the coils, you'll get a dipole in the far field, and having multiple coils, you can steer this around rather than having to rotate the satellite in order to do that. And then once you do that, you can probably do the things that you would expect. You can attract. You can repel. The animator did not understand the concern about collision, but that's all right. But after a little bit of thinking, actually you can shear. But by putting the magnetic fields perpendicular, but you're putting angular momentum into the array, so where's that conservation of angular momentum when you're only having internal forces and torques? It would lead to an unbalanced torque on the spacecraft, which would cause angular momentum to be stored in the rotation of the spacecraft, which if this is a telescope of some sort might not be good. So you can store it in reaction wheels. Another device that is driven by electricity. So now we could do, we could control all of the relative degrees of freedom between end satellites in an array without using any propellant, as long as you stayed within a reasonable distance. And reasonable distances, if you used high temperature superconductors, were on hundreds of meters between adjacent satellites, which seemed like a decent distance to operate over. So that's an example of one of the technologies we said, okay, so how do you build one of these things? Well, that's a good question. We built them. These were in the lab. They float on an air table. Liquid nitrogen gets put in here to keep the high temperature superconductors cold, and that feeds up around these coils, and they sort of come out those chimneys at the top, the nitrogen. So that was a case where my team looked at a problem, saw sort of a unique structure that we might be able to exploit in the problem, and then figure out how we can develop a control system which was sensors and actuators in this case, that could help us maybe make a more efficient system. So that's why I call this exploiting structure. And if you look at the top center for the controls people in the room, you're used to seeing, first day of a controls class, you get the plant, G of S, you get the controller, H of S. It's kind of a generic description of a plant. I do think of myself as a controls professor, but I don't teach the fundamentals of control. I try to find interesting structure in G of S that I can exploit in implementing the controller. So there's some other examples here in the upper left. I sort of grew up academically in the era of the Control of Flexible Structures program, Control Structure Interaction. You probably remember that from the 80s. And a lot of people were building up models, then using that to design controllers. The classic way is finite element models. So I took a little different look at it, and I said, instead of thinking this as a vibrating structure with modes and so forth, I'm going to think of it as an interconnection of waveguides, where structural waves would ripple up and down the structure. They'd come to discontinuities. They'd scatter, which means they reflect, they transmit, things like that. And instead of doing modal control, I'm going to do transmission control or impedance control, and think about how can I actively change reflection and transmission at junctions and structures as waves go around. And that's just showing sort of a open versus closed loop performance. But what was very interesting is this is where I learned about things like half integrators, quarter differentiators, and how to wire them together. I had this big analog computer. The thing weighed about 3 tons. But it was a great way with all the banana plugs and building these circuits to make this work. And these weren't solutions that came out of a natural sort of modal description of the structure. They were buried in there. It's the same sort of underlying physics, but it was a different way to look at the problem. Another one I looked at, I worked with University of Arizona, Roger Angel, for a number of years on adaptive optics, ground-based adaptive optics. And my students identified that when you look at the actuators and the sensors that were behind the mirror, there was a symmetry to it. And actually, the way Roger Angel designed these, there was 6-fold symmetry. You could pick up the mirror, rotate it 60 degrees, set it down, and you couldn't tell that it rotated. And that has a feature called circulance symmetry. And what it allowed us to do is to take a look at how to implement a modern state-space controller, which was computationally enormously expensive, and be able to simplify it so that it could run about as fast as like a simple CISO co-located controller. And so you could get a lot more capability out of the controller without having to spend the computational resources on it or sacrifice speed. And that was another interesting way to look at a problem and think about how how you could exploit structure in that problem in the control design. Also work on reconfigurable constellations that I mentioned before to see how you can dramatically improve regional persistence over doing static constellations. And then recently graduated a PhD coming back to this propellantless formation flight and saying, what else could we do magnetically? So this probably looks like James Webb to you with electricity rippling through it. But the idea is, you could remove a lot of structure here. You could, not saying this is easy, not saying this is cheap, but you could do it. and there might be some benefits. You could formation fly the secondary in front of the primary. My predecessor at Cornell, Mason Peck, has looked at flux pinning and how to hold things in close proximity if they're very cold, which James Webb is very cold. So you can use superconductors. You can actually separate the mirror from the warm spacecraft and the structure, but then you say, how do you get the power through? Well, you can actually use these coils to do inductive coupling for wireless power transfer. So there's a lot of very interesting things you could do here that don't really have traceability for how we do things in 1G with big telescopes. So I said I want to use our electromagnetic formation flight as sort of a theme through here. So we built it, and here it is. We have it floating on a platform on an air table here, and the one in the back is sort of bolted down. It has about 10 amps going through its. No, it's got 100 amps going through 100 turns, so it's 10,000 amp turns, and then the one in the foreground, we're running the coil through there, and he's pushing it, and it's doing control, basically to electromagnetically control the relative degrees of freedom between those two vehicles. Now, one could say, and one should say, that, yeah, you got rid of a consumable called propellant, and you replace it with a consumable called a cryogen. So, good point. What we have been able to do is turn this into use cryogenic heat pipes to actually now cool it using liquid nitrogen, the phase transition in nitrogen, in order to wick the heat to a cryocooler. So we have a separate test bed where we've been able to demonstrate that you can do the thermal control electrically. And if you're on something like James Webb, it sort of comes with the telescope, so that it comes for free. The cold comes for free. So let me step back before so this is not an ad for the upcoming movie. But before I talk about our on-orbit validation work, I wanted to step back to this Capstone course that in 1999 I was asked to set up. And we were thinking, okay, it's going to be a project, hands-on course. It's supposed to give you the students experience in building the life cycle of an aerospace product, and it's a space course, so it's got to be a space product. And so I was thinking, what's going to be the topic? And after talking with a few people, we came up with this. It was inspired by this one. And in fact, the first day of the class, I had actually rented, yes, I went out to a store, rented a VHS tape. We don't do that anymore, I don't think. But I rented this one. And I hope that's not too loud. But as you probably all recognize this, but I showed the students, I want 3 of those, and I want them to be able to fly inside shuttle or inside station, which I don't even think the first element had launched yet on station. But I don't want the little directed energy pieces out of the little zaps of lasers. And then I hit the pause button, and then they all booed. But I said, okay, so how are we going to do this? And so what we did was we actually sat down through the process, taught them the requirements, and going through a requirements review, PDR, CDR, and that was sort of the kickoff of a capstone class, multi-semester capstone class that we've been running for quite a while, a decade and a half now. And so upper left is where, remember, operate is part of conceive, design, implement, and operate. There's myself and our new deputy administrator, David Newman, on the left with the class flying on the KC-135, thanks to Goddard. So thank you very much for that. We actually got to fly the whole class. It was a small class. But we got to fly the whole class so that was a big motivator, I'll tell you. But it was a wonderful experience. And those were the first 2 vehicles that we built. And then since then, we built our electromagnetics that way and a number of other things. And actually, there's more over here. We've moved into small satellites. We had one micromass, which is atmospheric microwave radiometer. I think it's the first dual spinning CubeSat. And then one of the most recent instruments that we incubated through this class is Rexus, which is the regolith X-ray imaging spectrometer, which is flying on Osiris. And so there's been actually about 1/3 of these projects have actually made it into space. And that we're proud of that. I'm going back in time here and showing you a little bit about EMFF again, but showing you sort of the first version of it. And I call this build it wrong, then build it right. And the idea is that, you know, we can analyze problems forever. At some point, we got to go test, because analysis is additive. We put in the things that we think are needed, but testing is very different. All the problems are there, and you got to discover which ones you've missed and make sure you're going to deal with them. So when building it wrong, the first thing you do is you make a big dewar of liquid nitrogen that is open, and you stick it on the top of a very fragile vehicle and let it float around the lab, which is exciting. But the vehicle was pretty mean looking. You'll notice on the right, the student there is looking very fashionable in their safety goggles. So we have a little bit of safety training. Like most men, you know, save the hairline first. So, but I was also teaching. One of the students was assigned with the job of writing the safety document. So I went into the classroom, and he's typing away, 60 pages of it already. I'm like, wow, this is big. Let's go into the lab for a moment. And I took him in the lab, found another student who was trying to touch the liquid nitrogen, doing it real fast, because that way he wouldn't hurt himself. And I'm like, so I asked the student who's writing the 60-page document, I said, is this keeping this idiot safe? You know, you got to think about safety more in a real-life context rather than just how many pages in a document. And you know, at this point, we were just trying to make the thing work and see, these were open loop tests. We had a little bit of reaction, a little bit of control. This is interesting because, remember I talked about how if you start moving sideways, you're putting angular momentum into the array, but angular momentum's conserved. And so we're storing it by spinning the vehicle, which means you have to de-spin the magnetic field vector. So we're moving the current from that edge on coil to that one to that one. So it's like commutating a motor. It was an interesting challenge. But that was a lot of fun. But so now I want to go into on-orbit validation. How do we mature this technology and at the same time give students an education on how to do flight programs and do it within a period that is commensurate with their graduate program? So over the years, we've actually developed a number of microgravity technology facilities that have flown. And I categorize them in 3 types of facilities. Our mode facility stood for Mid-Deck Zero Gravity Dynamics Experiment. The first flight of that was on shuttle in 1991. And it was really a dynamics facility. And all of these were like laboratories or facilities. They all operated inside either shuttle mid-deck or inside station for a reason I'll tell you a little later. Then we added active control to that in our mid-deck active control experiment. And then recently we've been doing, well, it's not so recently, we're about to hit the 1 decade mark on our synchronized position, hold, engage, reorient experimental satellites, which Slashdot, I'm not sure what Slashdot is, said was the world's worst acronym. But that's okay. I think any news is good news. But Spheres is a formation flight facility that we've been operating on station for now about a decade. And it came out of that first Capstone class. So the first 2 facilities, Mode and Mace, these just show some pictures. This before we had great, real live video coming down from station. But the way we think of these labs is that they're like wind tunnels. They're analogous to a wind tunnel in the sense that it's analogous because we're not blowing wind over them or air over them. It's actually a microgravity type of wind tunnel. And the analogy is that it's an environment, it's a safe environment in which you can test a new technology in its formative stage without taking risk to the vehicle, to the environment, or to the operator. And so a number of things we did fluid slosh, that's sort of shown in the upper left, truss structure dynamics, human motion, sort of the forces and torques that that humans impart on a microgravity laboratory. They're shown here. That flew on shuttle and then flew on Mir. That was actually Dava Newman's, one of her projects. And then added dynamic control to it through MACE. That's shown on the right. It was actually the first, it was reflown on station as the first crew interactive experiment on station. Here's Bill Shepard, and Susan Helms also got to operate that. So the nice thing here is we could fly, shuttle would land, we could refurbish, we could change out different hardware. It was modular in nature, and we could refly and do new science at a fraction of the cost. So not only did we do this, we also codified a series of design principles for building and operating research laboratories in a remote environment such as ISS. And that's really sort of guided how we've done subsequent facilities. And so here's the Spheres facility, which is still operating. It came out of the Capstone class. We built it wrong. Then we built it right. We learned what worked and what didn't work in the original design. And then we went through the standard process for a flight program, went through CDR. That's where you start cutting metal. So stop changing things. So 2 weeks later, I violated that rule and came in and said, I want to change just one thing. And so I'm that requirements creep, yes. So I had to teach the students what that's about. So I said, there's an open face here. I want a plug that provides data and power, and then just put a plate over it. And I don't know what I want it for, I just know I want it. So I got a lot of heat for that, but they did that. And so that's actually allowed us to do just more than just formation flight, which is shown in the upper left. We really sort of developed this facility to look at satellite formation flight for sparse aperture arrays and things like that, collision avoidance algorithms in 3 dimensions. But now we could actually add new hardware. So over time, top center, we're hitting the 2-year anniversary of doing vision-based navigation and characterization of other objects, including tumbling objects, inside the space station. So you see the one is on the left is sporting a set of what we call goggles, which gives us stereo vision. And then we're creating sort of different target fields on that second sphere there. We've also taken EMFF up there, the electromagnetics. That's called RINGS. That's headed by the University of Maryland. And the spheres are in the center there, but now we're working on electromagnetic formation control as well as wireless power transfer between the vehicles. Just recently, maybe about in the spring of this year, we put on docking ports so we can start doing hard docking and undocking. And in particular, what we want to do is look at docking and undocking with tumbling objects. So there's different complexity of tumbling. If anyone's seen Interstellar, there's a particularly exciting scene there about docking with a tumbling object. And it's Matt Damon's fault. I won't tell you anymore. But it's, so here, unlike Interstellar, we can do this in a very risk-tolerant yet 3-dimensional environment and try to dock with tumbling or nutating objects and things like that. So that's just starting up. There's also been a program with Florida Institute of Technology, led by them, who doing fluid slosh and microgravity. And now we not only use the pieces like the vision capture and the various inertial measurements that we can take, but we can to characterize what the fluid's doing. But we can also start looking at how can we use these to kind of control a vehicle that has a high fluid mass fraction. And the uncertainty of the slosh dynamics that provides. And then upcoming, but still hasn't launched, is actually being able to put together multiple dockings in order to look at robotic assembly of vehicles in a microgravity environment. This just happens to be an image where we've got CMGs that are attached to one of the spheres, and getting that into the 3D environment would also be useful. I'd say we pride ourselves with the most collisions with space station. We've had thousands, probably. For all of you with your microgravity experiments up there, my apologies. But we've always formation flown, but in the beast of inside the belly of space station. So here's a couple examples. This is an example where we're working on array aggregation. This is sped up. Greg Chamatov has not had too much caffeine. This is just sped up. But it's a very simplistic controller. It's called cyclic pursuit, which is a leader-follower kind of thing, but it's interesting to see how that behavior evolves as you test. This is a very early movie from our vision-based navigation, but I like this because it looks like an old Star Trek episode where some alien, what's that? Tron? Where they beamed in the vehicle to go interrogate the interior of the Enterprise or something like that. But this is in the Kibo module, and over here is what the computer's thinking. It's identifying the geometric center and then using that to navigate around the other object. Since then, we've been navigating around tumbling objects and are able to identify what their inertia ratios are, what their spin axis orientation is, identifying features on the surface and doing things like that. Greg Chamatov, who you saw there earlier, and actually Srija helped us a lot on this program, he came back from station and he said, you know, so you've designed it so the technology that you are testing, which is command and control software, is not a safety hazard. And that allows you to redesign quickly and get new code up and test it out. And we go, yep, that's right. Make sure that you satisfy safety by other means other than the technology that you're trying to test. So he said, so anyone could program it to do anything and it doesn't matter. We said, yeah, where you going, Greg? And he said, so why not let high school kids program them? So we said, sure. So we created a program called Zero Robotics, and yes, it's a play on FIRST Robotics. You've heard of FIRST?
Yep.
Okay. We just wanted to get one ahead in the sequence. So we went with Zero Robotics, and it means two things. I always thought, well, you know, it's zero gravity, that makes sense. But the actual thought leader behind this program, Dr. Alvar Sanzotero, who's now running my lab, what's his lab? He said, but the zero is also for zero cost. So that the teams could get together, and as long as they have an internet connection, it's free. It's their time and their effort, but it's dollar-wise, it's zero. So we started back in 2009 with 2 schools in the very northern tip of Idaho. That's a long story. Actually, my student that was leading this development was from there, and his dad led a FIRST Robotics team, and there was a friend of the dad that actually gave us like $20K from her company to help us get started on this idea, and also was leading a FIRST Robotics team, so it's kind of in the family, so we got those 2 schools to sort of compete. And since then, over the years, we've grown it, and this is an old slide. It only goes through 2011. But it's gone international, so it's the US, it's Europe, and boy, the Italian high school teams are good. But it's, I think we now have some from Russia, we're bringing on Australia, and we're bringing on Mexico, and it's really expanding pretty fast. And it's I think it's a great opportunity. The way I think about it, it's the only high school STEM arena-style sort of robotics competition that's off the planet. And so it's, and the other thing is they get astronauts to work for them. So we actually project on you can see in the center top there, the finals are live. The astronauts call the play-by-play. It's a head-to-head kind of competition. There's a game they're trying to achieve, and there's screaming, there's crying, there's all the above. So it's an exciting competition, and we also now open that up to a middle school activity, and all the sort of coursework and learning material is online, and all the simulations are online, and if you want to mentor a team, please get involved. All you have to do is go to Zero Robotics. So then I've ended up, as I said, I wanted my service to be outside of MIT. I'd been there a little too long. And actually, when I arrived at MIT in 1978, this seems to be little known to a lot of people at NASA, is Kendall Square in Cambridge, Massachusetts was kind of depressed. There were a lot of empty lots and weeds growing. And I said, why is that? And they said, well, it used to be a NASA center. It used to be a NASA center. It was the Center for Avionics and Computing. And in fact, they built the main building, which is now the Volpe Department of Transportation building. But it's the only NASA center, I guess, that had ever been closed. So my government service has really been mostly in three areas. One is the for the Air Force through what's called the Air Force Scientific Advisory Board. Another is through LIGO, which is ground-based gravity wave detection, and advanced LIGO, which is really NSF funded, that's government. And then NASA. So I'll just step through a few of these, just show you some of the details. The Air Force SAB was a wonderful experience. I don't know if many of you know about it, but it's unique in the sense that it's an advisory board that has been around 2 years longer than the agency it advises. So they had their priorities right. But I think in something like with the Air Force started in 1949, I think, separated from the Army Air Corps. And this started in 1947 it was sort of the brainchild of Hap Arnold and Theodore von Karman, who said that the Air Force of all the services, I could step in hot water here. The Air Force among all the services is the most dependent on high technology and science, and therefore needs an organization to help advise them in this way. So they do two things each year. One is they review the Air Force Research Lab, which is about a $4.5 billion annual investment across 9 different directorates. I had the opportunity to lead that annual review for 3 years. And then they do that in the fall, and then in the spring, they do studies at the request of the chief and the secretary. And these are particular studies I was involved in. Future of launch, sustaining aging aircraft. I mean, that was wonderful, just crawling through all kinds of planes, a lot of travel here. And it's sort of sad. It's like they're all in the ICU or something. But actually got the opportunity to see the last 8 F-22s coming off the assembly line, and they were already considered aging aircraft because vendors were vanishing, corrosion issues, things like that. Another particularly interesting one is this extended use of aft space sensors. It's a little cryptic for certain reasons, but it's the idea of saying when we have a new mission that requires space capabilities, do we really always need to build a new satellite or set of satellites to achieve that? Could we instead take data sets from things we have and combine them in ways that we haven't done before in order to give us information that is needed for that new mission? And there were, I think Goddard probably thinks about that problem a lot. We came up and visited here. And, there are some interesting things you can do there. And then also the last one I was on microsatellite mission applications. My NASA advisory time was quite actually extended throughout my career. There's probably 2 themes you would see here. One is telescopes and technology for telescopes. That seems to be the area that I've mostly focused on. But you'll also see a little bit of Mars. That's the Mars Exploration Program System Engineering Team, and ISS research. So that's sort of, obviously it'd be on the panels that your background would support. So I found that very useful in understanding what the real applications were. And then for the last year and a half, I've had the wonderful opportunity of being able to really stick my head under the hood of NASA and see what's going on. These are just the 2 offices that are in the Office of the Chief Technologist. I sort of think of it as right half, left half brain. This is the very sort of, which is which? This is the left half brain. That's the intellectual sort of, this is the right half brain, the innovation, the weird ideas, yeah, that kind of thing. So I think it's a great combination to have in that office. So as Chief Technologist, these are really my objectives. One of the things every day I would see 10 things I thought I could help with, and then there'd be another day and another 10 things, and as I was warned, don't, try to stay with just a subset. So one thing that I found extraordinarily surprising is the access that I have to the leadership of the agency. It really opened to frank discussions. I'd have meeting with Robert Lightfoot, thinking it's going to be in an auditorium this big. I'll sit in the back seat, bring a sandwich, and then I find out, no, it's a one-on-one meeting with Robert Lightfoot. And it's an opportunity to bring fresh perspective, and I think the A suite is very enlightened in this way to bring people from the outside for the chief technologist and the chief scientist, as well as other people, select areas in NASA, in order to bring some outside perspective to what NASA's doing. So one of the things I asked is, as we're making tough decisions in what technology should we invest in, what engineering facilities should we maintain, or which ones should we divest, what workforce skill mix should we have, I sort of brought up the idea that, it depends on what we're trying to do. And that tends to be driven by architecture. What are the missions we're trying to do? What do we need in order to build these things? And so that's one area. There's also, you've probably heard of the Valley of Death. How do we get across, how do we take a technology that's been developed to a certain level and actually give it the opportunity to fly so that people will then trust it? And I think we are in a period with ISS and nanosatellites and UAVs and so forth, that there are a number of low-cost platforms that get us into authentic flight environments that can help us to bridge that somewhat. Also, this is always an issue about how to sustain the technology investment. It's kind of it's the foundation for all that we do in the missions we build, but that it's not the thing that gets the press. So how do we help to get that message that technology is essential to everything we do at NASA? And then also engage the broader community. And how do we collaborate with OGAs most effectively, industry and academia, and maintain an awareness of what's going on elsewhere so we don't replicate it or duplicate it. When I first accepted the job, I was eating breakfast and my wife said, what does a chief technologist do? And I sort of stammered for about 20 minutes. And she said, you're probably going to have to be able to answer that one. And so I said, okay. So I worked on it for a little bit. And I thought a good way was technology creates tools that go in a toolbox. Engineers use those tools to build the missions that the scientists need to fly and help answer those scientific questions. And so better tools mean you can build better missions. And so that's what technology does, is it puts those better tools into the toolbox. So then, the technology resources available are limited. They're precious. So we often worry about how much is it going to cost to develop a technology. So I said that the technologists can tell you how much it will likely cost. They'll probably get it a little wrong. But that's only half the story. The architecture tells you what it's worth. So just because it's expensive doesn't mean that we should shy away from it. It really depends on what it's worth to the mission. And that's where architecture can play an important role to give you that return on investment. So I was going to focus on that a little bit to close. I sort of had the feeling, I saw in pockets at NASA that these three organizations, engineering, technology, and science, are a bit stovepipe, but at other places there's very good dialogue. So I just want to emphasize that I think it's important that we have a strong dialogue among these three organizations. I mean, in my office we've got a Chief Technologist Council. They're very helpful. There's an Engineering Management Board. There's a Chief Scientist Council. But we need to make sure that we are talking between each other, because you can see that there's different sort of timescales. Science and engineering, that's where we build the missions. The scientists create the requirements, the engineers build to those requirements, but you have to have a discussion in order to trade requirements so that you make sure that the requirements are actually affordable, meeting the requirements is affordable. There's also a discussion across here which is very valuable, engineering and technology. As we think about vanishing vendors and challenges with reaction wheels, what are our biggest challenges recently? A bunch of different challenges, but sometimes the idea is we should help boost the vendors that provide essential essential capabilities to us. But at other times, we ought to think about, well, should we give that up and find a new way to solve this problem? And I think that's an important sort of midterm. If that one's a near-term conversation, building the missions, this is kind of a midterm conversation about how do we maintain the space industrial base versus how do we bring in new capabilities because old capabilities are vanishing and, in fact, may not be adequate to build the missions. And then this conversation tells us, so that's sort of the blue sky conversation. So as I seem to have found out that when we do these decadal studies, to get into the decadal study, you need to have a certain level of technology readiness to be considered for a decadal study. So unless we have this sort of conversation between what is the art of the possible, then we really aren't making those jumps into new capabilities as quickly as we should. So I also think architecture is kind of the central theme as a way to think about this. Answer these questions in the context of the types of missions that we're trying to achieve. So one of the things I've brought up in my time here is that think about the journey to Mars. We're talking about the president challenged us in the mid-2030s to orbit Mars, and then a landing will follow. That's a long time from now. That's 2 decades, and changes occur every year. Call it budget, call it failures of things, call it new scientific discoveries or inventions of technology. So we need to be able to, we need an architecture for getting to Mars that is resilient to the changes that are going to occur along the way. It'd be great if we knew what all the changes were going to be up front, but we won't. We'll be partially executed through this architecture, and then our assumptions that we made at the beginning are going to turn out to be false. What do we do about that? Well, when I looked up in Webster's dictionary, resiliency means the ability to recover from, sort of be robust or adaptable to change. So as I've been looking through the architecture, if you look at a roadmap of how to get to Mars, there's Earth in the bottom left, Mars in the upper right. There's many ways to get to Mars. There's many more ways than there probably were to get to the moon, yet we almost missed John Hubble's lunar orbit rendezvous. So how many of those sort of Hubble insights are we missing now? So when I look at the architectures, every week there's some study, there's some presentation. There's actually the 40 Mars talks are happening this week, later this week at GW. Right now, in Earth-reliant phase, we have one architecture, station, commercial crew, commercial cargo, and we're executing that. But if you look out in the 2030s at Earth-independent, there are 20 to 30 different architectures. We cannot afford all the engineering and all the technology investments to keep those all viable. We need to narrow that space. And so in this fiscal year, we're going to try to narrow that space so that we can align investments. In turn, what we're going to do at the proving ground, which is kind of like Project Gemini, that's where you take the tools you developed during Mercury and put them into ConOps and make sure they work reliably enough so that you can go to the moon. Well, that's kind of the same construct here. As we narrow the space for what we're going to do, for how we're going to get to Mars, we will in turn narrow the space for what are the things we need to, what risks do we need to reduce in the proving ground in cislunar space. So this is just sort of my way to work through architectural resiliency. I think I'm running out of time. I think I well ran out of time. But so I'd be happy to talk to you about that. It looks like a feedback diagram. It's probably not a surprise. But the idea is how can we narrow to a class of architectures so that as budgets change or policy changes or we have failures and discoveries, how can we accommodate those in the most cost-effective way possible? So if you have ideas along that line, I would love to hear them. Give you some closing thoughts here. I think we all need to be systems engineers to some level. I like to use the phrase, an optimized system is not simply the sum of optimized parts. You got to think across the whole sort of the whole system to see how pieces move, how pieces, interfaces matter, see how pieces fit together. Maintaining balance. I think government, academia, and industry all play essential critical path roles. And I think we got to make sure that we keep that balance and in that teaming relationship. Actually, if you look back at the start of NASA, Glennon, I think the first administrator, actually said we needed to build up NASA fast and set up large programs at major universities because they had the facilities, and that way they could they could hit the ground running with NASA. So I think we need to maintain that balance because they all bring unique and important features to the mix. The last part is thought leadership. I've had, in looking at AFRL and going in, what I sort of call the review of AFRL a wire brush scrubbing. They loved it. but it was, I think it's a very, very useful process. But we would find that you could tell leaders of different programs, you could sort of see differences in their attributes. Some, I'm not going to name any names, were a little sort of skin deep on their knowledge of what was going on in the organization, and that was a concern. But others just knew everything about their organization. They had this vibrancy about it. They worked with their team. We'd go visit their labs, and you could just see that this was not a very hierarchic organization. It was one that was very flat. The thought leaders created that vision. They engaged with their team in a two-way dialogue, not just sort of flow down of do this, do that. I think pretty important, they instill an urgency to their team that to get the job done and meet the needs of the Air Force, and I think instilling urgency is an important thing in all of aerospace, and that there is no job that the thought leader can't do. You need to be able to identify those things that need to be done and show that you have a willingness to do them, and that sets an example for your team. So I'm going to stop there and say thank you, and if there's any questions, I'd be happy to entertain them.
Okay, very good. Let's give it.